All right, line A1, learning task 3, we're going to take a look at solving a couple of problems just based on trigonometry over here. And really what this lesson is it's just basic, simple math that we're going to be using a lot of Pythagoras for so that we can go and find different values. In order to do so, in order to make it applicable to electrical, or actually, to go and make what we're doing in electrical applicable to this, we need to understand a couple of different types of triangles that we're going to go and have. We're going to have two main types of triangles that we're going to work with throughout this year. One of them is going to go and be the impedance triangle, or the Z that we have, which is going to be impedance. We'll learn exactly what that is later on. The other one is going to go and be my power triangle, which is going to go and deal with real types of power as well as with what we refer to as quadrature types of power, which are almost like a fake power, but they aren't, they're real, and we'll explain exactly what each of those components are later on. For now, we're just going to treat them as triangles. We'll explain where all these different values are on the triangles, and then after that, then we can go and solve values based upon these. What we'll use is we'll just use an analogy right now to go and describe our impedance triangle. This is the one that I prefer to go and use. Consider it biking uphill against a headwind. You know that if you've ever ridden on a pedal bike before, if you're riding up a hill, you're fighting against the force of gravity, right? It's harder to go and pedal that bike uphill. Now, if you got a headwind going opposite against you, then you are going to be fighting that as well. And so what you're going to go and find is that you, on your bicycle over here, are going to go and be fighting, that's a terrible drawing, but you're going to be fighting against what we would refer to as being a vector sum of these two. The headwind fighting against you and the gravity, and all together you get this opposition to movement. When you're on your bicycle, you can never actually differentiate and say, well, this much force that I'm putting out must be the gravity and this much must be opposite to the headwind. You can't do that. You just feel that combination of drag on you that you're trying to fight your way up and against. We're going to go and have something very similar inside of an electrical circuit. And the thing that we're going to have is going to be this thing that's going to be called impedance. And impedance is going to go and be a vector sum, so adding together two dissimilar types, just like we got gravity and headwind. We are now going to go and add together resistance, pure ohmic resistance, which we have dealt with before, and this other new value that we're going to go and learn about, which is going to go and be reactants, which is going to be the way that an inductor or a capacitor creates opposition to any sort of a current flow. And it's all going to be heavy electrical theory, and we're going to cover that once we get into these actual components. But for now, you just need to know that there is going to go and be some sort of an opposition to current flow that's going to be created by my inductors and my capacitors. So we're going to call those components since we haven't explained what they are. Components. And we are going to go and have resistance, which is going to be my R is equal to K times L over top of my CMA. This should be a formula that's familiar with you from first year, which was that resistance is equal to the constant, the material type, multiplied by the length of the material, all divided by the circular mill area of the material. Describes physical properties. These ones over here are going to be magnetic or electrostatic properties that are going to go and create those. Together, they're going to go and give us a vector sum, which we are going to go and refer to as being our impedance, or Z, which is going to be the sum of both of these together. You need to know what these values themselves are going to be on the triangle. Anytime that I'm looking at resistance, resistance is always, always, always on my x-axis. Anytime that I'm looking at reactance, and it's going to be XL, or sometimes it's going to go and be XC that we are going to have, reactance is always going to be on the y-axis, and then the impedance is always going to be the hypotenuse between those two. Once you've got all of that established, you can just go and change your Pythagoras theorem into these impedance values. If you take a look at the bottom of the page, they show that our Z, our impedance, is going to be equal to our R squared plus our x squared, all square rooted. And then the rest of them are just going to be derivatives of that as well. Then they go through a number of examples. We'll check through a couple of these examples. The bulk of them are going to be for you to go through on your own because it's simple math, once again, that we're doing. We're just giving it new values that we are going to go and have off of these. So they're saying, for example number 1, solve for an impedance when I have got 30 ohms of resistance and I've got 40 ohms of reactance that I'm going to go and have. So what I can do is I can now go and add those two up. I know that Z is going to be equal to my R squared plus my X squared, all square rooted. I just substitute in values for R. I'm going to go and put in 30. For x, I'm going to go and put in 40, and then I'm going to be able to solve that for my z. You should once again recognize this 3, 4, 5 triangle, but hey, let's just go follow through it there. Second root, bracket. I like to double bracket everything because it's just going to be safer that way. 30 squared plus 40 squared. Ooh, that's one too many brackets. We'll delete one, which gets me a value of 50 that I'm going to go and have. So I have got a value of 50 over here. We're going to come back to these calculations later on. We're going to show you some shortcuts on the calculator that you can use to get to the same ones, but they should not be relied on as being absolutes. You do want to make sure that you're able to do this the old-fashioned way through Pythagoras. The next one that they give you is going to be where we've got a triangle, once again, impedance triangle over here, that has got a total impedance of 100, and it has a 50 ohm resistance that we would go and have. This one would be solvable as well. You would just go and say now that you're using the x formula. X is going to be equal to my hypotenuse, so my z, 100 squared, minus my r, 50 squared. When you do that, punch that through, you're going to go and end up with a value of 86.8 that you would get off of your x over there. We'll skip past example number 3. Let's go and talk about our next triangle that we are going to go and have. Our next triangle is going to be something called the power triangle. We will use these because they are going to go and tell us about the amount of useful work that we are going to be doing compared with the amount of apparent work that we are doing compared with the amount of reactive power that we are going to go and have. Once again, we are going to go and have something that we have dealt with before, watts. We covered those inside of first year, which was going to go and be my total amount of heat dissipated. Anytime we got a watt, doesn't matter where that watt is, that watt will ultimately be dissipated as heat. You know, whether that's going to be watts of heat dissipated into electromechanical braking, into heat that's coming off a transformer winding, into, you know, a light bulb that is generating heat, which is then converting to electricity. Any of these things are all going to be watts. True useful power. We've got this other one that is going to go and be our VARs, or what we refer to as our reactive power. Reactive power is going to be this type of power that moves back and forth inside of our circuit and causes heating effects inside of our circuit on like some of our conductors, causes magnetization, lagging power factor, a bunch of other stuff that we don't want to have, but it doesn't really do much useful. We can counteract it. We can find a way that we can go and, you know, deal with this, and we'll cover that later on in power factor correction. But when we have it inside of our circuit, it's just not awesome for the circuit. What we get altogether from the resistance, or from the watts that we are going to go and have, and from our VARs, is we're going to go and get what we call our apparent power, or our VA, volt amperes. And this is simply what we would get when we take our line voltage and our line current together. We multiply them together. It's not going to be true watts because there's some of that, you know, current that's going through to form our VARs, and some of it that's going through to our watts. So we just call this thing our VA. The easy way to go and describe them is to go and use the beer mug analogy. The beer mug analogy is simply just imagine a big mug of beer, and the total capacity, the size of your system, is your kVA size of your system. The amount of wasted capacity is anything taken up by VARs. They're the foam, they're the part that we don't want to go and have. The useful work is going to go and be inside of our watts that we are going to go and have on that system. And it's going to be a ratio of those two, the amount of good to the amount of bad, that is really going to go and determine when we have got something that we would term as being good power factor versus poor power factor. We want to have maximum watts that we are going to go and have, and minimum VARs that we are going to go and have, because once again, our system capacity is going to be tagged out as being that VA. This one over here on the right, we got way too much VARs inside of the system, way too little useful work. It's not an efficient system, and it is not something that you want to be paying money for. Once again, you're going to be billed based upon VA, the size of your system, or what it appears to be have going through your meter. Both of these two systems, if I were to go and talk electrically, would have the same VA, which would mean that I would get billed for both of these the same. If you go to a pub, back in pre-COVID days, and you bought this beer, and your buddy bought this beer, he would be getting a way worse deal than you off of that one compared to, you know, yours that you would have over here. So it's simply just going to be, once again, a measurement or a combination of the two of them. We're going to go and call this thing, once again, a vector sum, or VA, that we are going to have of our VARs and our watts. And we see that off of these triangles. That's it for beautiful color illustrations. Now we're going to go back to our triangles over here. And we're going to discuss the fact that this is a right angle triangle. And therefore, Pythagorean is going to go and work out on this one as well. With this means that if we examine it, we should identify this one as being our hypotenuse and these two as just being our adjacent sides that we are going to have, which tells us that our VA is going to be equal to our watts squared plus our vars squared, and then we take the square root of that entire mess. That's going to go and give us our total volt-amperes of our system. From that, we can go and derive the rest of our formulas out of there as well, right? We can see that if we were looking for watts would be equal to my VA squared, my hypotenuse squared, minus my vars squared, all square rooted. Or if I was looking for my vars would be equal to my VA squared minus my watts squared. Any one of these is just derivatives of Pythagoras' theorem. So we can go and use them to go and calculate anything that we are going to have missing from those triangles. Let's take a look at example number 4. It says, look, if we've got 500 watts and 500 vars, what would be my total amount of VA for a system? So this value was 500, and if this value was 500, what's my total VA going to be? Well, I'm going to have to use this formula over here. So let's go and do that. And there, because we're adding the two short sides, we have to do the addition. Oh, I forgot a bracket there at the beginning, so we'll just go back to the very beginning. Add one more into the front there. There we go. 500 squared plus another 500 squared, which gets us out to a value of 707 VA that we would have. 707 VA. The other ones are just going to be derivatives of this. Example number 5 talks about one where we have the VA 500 and we have got the watts 300, but then we want to know the vars. So in that case, we would be using this formula over here. Do 500 squared minus 300 squared. It's going to kick you out to your answer of 400. Notice that it's 3, 4, 5 triangle over here again. And then the last example that they have, example number 6, talks about now kilowatts. Now, kilowatts is a term that we haven't dealt with yet this year, so let's just quickly discuss what it is. Kilowatts means thousands of watts. So it says, what's the kilowatt input to a motor drawing 12 kVA and having 9.6 kVAR reactant? Remember that watts are the true useful amount of work. So they're saying that I've got a motor that has got 12 kVA. This is thousands of volt amperes, so I can just take out the K and multiply this by 1,000, 12,000 VA, and it's got 9.6 kVAR that I have. Once again, I can convert this thing, take the K's out, which means thousands, and that would now be 9,600 VARs. And it wants to know what's the total amount of watts that I'm going to go and have out of here. If you were to go and take that, you'd be looking at this formula over here. Take your VA squared, 12,000 squared, minus my VARs, 9,600 squared, and that's going to go and give you a total amount of kilowatts. Total amount of kilowatts that you would actually calculate out of this thing would be 7,200 watts, also known as 7.2 kilowatts that you would have off of there. All right, there's an exercise number 1. They give you a table for an impedance value triangle. They give you a table for a power triangle. Go through, calculate those ones. There's 5 of them each. Once again, shouldn't take you very long. It's just practice with Pythagoras. Make sure that you're ready to proceed into our second year materials. I'll pause for a second. You go and do those as well. All right. Let's talk about solving impedance and power triangles. What we have is we are going to go and have triangles that for a circuit are going to go and be the same. If you look at both of these, you see that they're both right angle triangles. You see that they have both got a true power type of value that's going to be on the bottom. We're going to have resistance that we develop our true watts from over there. We are going to go and have our reactants, which we haven't covered yet, but we're going to learn that we develop our VARs from our reactants. And then right over here, we're going to go and have our impedance, which is where we're going to go and develop our VA from. So we've got all of these values that are going to be similar. For a single component, if I were to go and have a motor, if I had this triangle for the motor, the beautiful thing is that that triangle for the motor, the impedance triangle, would be able to go and spit out a power triangle for that motor as well. They're going to go and have what we refer to as the same phase angle, which is going to be this angle theta that's going to be inside of here. Now, we're not going to do these conversions yet, but you need to know that this is coming up so that if I gave you a motor and if I gave you two values out of any one of these triangles over here, let's say that I gave you theta and I gave you resistance, you would be able to go and develop out this, and as long as you then had at least one value from this triangle, you would be able to go and take angles calculated in this one and carry them through into the other triangle, which is really how we get to a lot of our solving later on. Sometimes we will only see a single value for a triangle, and what we need to know is we need to know that if it's a triangle to do with a piece of equipment, if it's a power triangle, that power triangle is going to be the same as the impedance triangle for that same piece of equipment. So we'll have to go back maybe into the impedance one where we've got multiple values and then take that through into our power one, etc. Let's go and move away from that concept yet, though, because we've got a bunch more base theory we have to cover for that. And let's just talk about two-value triangles over here. If I'm given two values, the first example they give us is 60 degrees, as well as an impedance of 10 ohms, I should be able to go and solve this multiple different ways. There's at least two ways to go and solve this that should be immediately apparent. That would be for me to go and use either my sine, my opposite, over my hypotenuse of 10, or my cosine, my adjacent, over top of my hypotenuse for this one. Either one of those would work. Let's go and say that we're going to go and work with, what did they work with? They decided to go and work with cosine. So they're going to be looking for the values of resistance. Oh yeah, I guess that's what the question asked. Sorry, reading too far ahead there. Looking for this resistance, let's find that resistance. We know that my cosine of theta is going to be equal to my adjacent over top of my hypotenuse. Okay, that's just the straight trigonometry formula that we've all grown up with inside of high school and stuff like that, middle school. What we know is then that now we no longer call them adjacent. We call this bottom section over here the R. We know that we call this section over here, instead of the hypotenuse, we call that the Z, and we know that this angle over here was 60 degrees. So what I can do is I can go and say that cos 60 is equal to R over top of Z, and my Z value I've got of 10 over here, which means that in reality I can go and bracket this whole thing and I can cross multiply this 10 up to this side over here, which would allow me to scratch it off the bottom over there, and I'd end up with a formula that says 10 times cos of 60 is going to go and give me my R value. You can either convert cos 60 into a decimal. If you convert it into a decimal, it will become 0.5. Or if you want, you can punch it directly into your calculator like this. We'll do it both ways because it's really, really quick and simple. We'll start by just taking cos of 60. If I take cos 60, we see that's 0.5. That's where this 0.5 comes from. So now I could go and say 10 times 0.5, which is going to be equal to a value of 5 that we could get for our R. So we could place that down there. Or alternatively, instead of doing that conversion and writing that down, we could go with the straight mathematical and say that 10 times cos 60. So I'm not even simplifying it down there. I'm just going to leave it in like that. It's equal to 5 as well. So either way, potato is going to go and get you into that. Once again, cosine of 60 is simply just a ratio of our two sines. Example number 2 asks us to go and find an angle, a power factor that is going to be associated with this. Is going to go and happen later on, where we're going to need to know circuit angles. And we've actually got a lot of equipment that is going to go and have angles designated onto it, and it'll make more sense once we get through second year, and particularly through the super heavy third year material that's going to be coming up for you in a bit. But let's go and deal with this one just in its simple form over here. They say, what's the phase angle for a circuit that has 250 VARs of reactive power? So we know we're working in this one here, 250 VARs and 800 watts of true power over here. I could Pythagoras, I could figure out a VA from this thing, but I don't need to go and figure out that VA from this one. What we're going to do instead is we're just going to go and kick this thing into tangent, because we know that the tangent, tan theta, is going to be equal to my opposite, 250, over top of my adjacent, 800, that I'm going to go and have over here. Now, here's where this gets a little bit tricky. We've got two values, two magnitudes, okay? We're looking at magnitudes that we have over here, and now we need to convert that into an angle. We haven't done that yet this year. So what we need to do is we need to go and ultimately do this whole cross-multiplying thing, right? We would have to go and take 800 up, tan theta down. Imagine that tan theta is over top of 1. And so what we would get is, if by the time I do all the cross-multiplying around back and forth inside of here, this whole formula would look like this red formula over here. It would say 800 over 250 is equal to 1 over top of, just write that. Sometimes I make little spelling mistakes as I'm writing tan theta that I would have over there. And that would be me just cross-multiplying everything back and forth over here. It's a bit of a pain to be able to go and do that, to have to go and do that. So what we can do, instead of doing this, which would give us then, 1 over tan theta, and then we would have to go and re-invert that whole thing to go and isolate the theta itself, what we're going to go and use is we're going to go and use what's called cotangent. And cotangent just basically allows us to, for the sake of simplicity, move just this over to the other side. And then we can just abandon the angle on this side, and we're going to go and have that physical angle over there. So what I'm going to do is I'm just going to go and take 1 over tangent. I'm not going to take 1 over tangent and the angle. I'm going to leave the angle over here, and I'm going to move this over to the other side. Now on your calculator, it is usually going to be written as tan negative 1 like that. You should recognize that anytime we see this negative 1 like that, that means the inverse, or 1 over tangent is really what that means over there. So we're going to go and take that 1 over 10, and we're going to move that onto this side over here. Let's do so. I'm just going to move these over a second. Just give me 2 seconds here with my marker. We're going to bracket that out. Tangent, cotangent there is equal to my theta. When we punch this in, it's going to spit out an actual angular degrees. Cotangent is going to be above tangent, so what you're going to have to do is hit second function, cotangent, make sure you bracket it, and then do 250 divided by 800, which gets you to a value of 17.35 degrees. 17.35 degrees. Okay. Go through that self-test and get familiar with how to go and do these operators, because what we're going to move into next is going to be starting to go and work with vectors. And then once we get past the vectors, then we're going to go into calculator usage for these, so that we can go and make some of these changes much faster, much easier.